last day of our wonderful conference, and it is my pleasure to introduce the first speaker of our morning session. This is Professor Tomoyuki Arakawa from Kyoto University, Japan, and he's give us a talk entitled Hilbert Schemes of the Points in the Plane and Quasi-Lisse Vertex Algebras with Fourth Symmetry.
First of all, I'd like to thank the organizers for giving me the opportunity to give a talk at this occasion. I'm very much honored to give a talk here. And I'd like to talk about a recent joint work with Toshiro Kuwabara in Tsukuba and Sven Mola in Hamburg. So I'd like to talk about something about vertex algebra. And vertex algebra is some algebraic system introduced by Borges in order to give a rigorous framework for a two-dimensional conformal field theory. So as you know, for quantum field theory of dimension greater than 2, there's no satisfactory mathematical definition. But in this two-dimensional theory, you can define give a rigorous mathematical definition using this vertex algebra. And this vertex algebra can be regarded as a generalization of infinite dimensional real algebra such as affine quasimodular algebras, because these define vertex algebra includes this kind of infinite dimensional real algebras. And so because it's originally designed to define this two-dimensional theory, it was not expected at all that this vertex algebra has anything to do with higher dimensional quantum field theory. But recently, people have discovered that the vertex algebra appear also in higher dimensional quantum field theory. And in such appearance, certain invariants of vertex algebra plays an important role. So this appearance, in fact, it's not unique way, but in several ways. And yes, and I'd like to talk about some invariant of vertex algebra. So if you are given vertex algebra, Yonchan Zhu defined a certain finitely generated Poisson algebra called Zhu-Schitz algebra. So it's natural to consider its spectrum, which we call the associated scheme. And mostly we are only interested in its topological structure as topological space. So we often consider its reduced scheme, which we call the associated variety. So this is a certain geometric invariant of a vertex algebra. And let me explain an example for let G be a complex simple real algebra. Then you can consider the affine corresponding affine quasimodular algebra. Then there exists a corresponding vertex algebra called universal affine vertex algebra, which is the representation of G hat, is just induced representation of G hat from one-dimensional representation of this parabolic subalgebra. So this has to be here. Which here, so here GT act as 0 and K act as, I forgot to say, the K is some complex number. And this has a structural vertex algebra. And you can talk about the representation of vertex algebra, and the representation of this vertex algebra is nothing but the smooth jihad module of level K. So smooth means that the x Tn m equals to 0 for sufficiently large n for elements in G. So representation of this vertex algebra is essentially the same as representation of this affine Katsumori algebra. So in this sense, this vertex algebra can be regarded as a version of enveloping algebra of G hat. And the associative variety of this vertex algebra is just G star, which correspond to the fact that this affine Katsumori algebra is affinization of this D algebra. And interesting happens when we consider the simple quotient of this induced module. Now this inherits vertex algebra structure from this one. So you can talk about representation and associative variety of this one. And representation of this vertex algebra form a full subcategory of this one, which can be a very interesting category. And associative variety is a conic and J-invariant subvariety of G star. So associative variety of this one is really analog of associative variety of primitive ideals of enveloping algebra of G. And but there is a difference because in the case of associative variety of primitive ideals of enveloping algebra, associative variety it was a closure of nilpotent orbit, which is contained with nilpotent cone. But this is not the case for the associative variety of affine Katsumori algebra. In fact, when this level is not rational, then this induced module is already simple, and so the associative variety is the whole space G star. And but there's another extreme case when associative variety is just a point. So this happens if and only if this representation is integrable as a G hat module. So this zero associativity condition characterizes integrability condition. So in general, we cannot really talk about the integrability for general vertex algebra, but using this zero associative variety condition, we can generalize this integrability for arbitrary vertex algebra. So this notion was called Lisse by Baylis and Feigen-Mezu in the case of Virasoro algebra. So they call a vertex algebra Lisse when this associative variety has a zero dimension. And it's known that this Lisse vertex algebra has very nice properties, such as so any simple V module is positive energy representation or highest weight representation. So this is very strong because if you consider any representation of G hat, there are many representation of affine Katsumori algebra, which is not highest weight. And if you talk about a simple representation of this vertex, the representation has to be always a highest weight. And also they are only finite in many simple modules. And also, if it's also rational, this means that if representation is completely reducible, the characters of simple modules form a vector-valued modular function. So this is also a very strong statement. So if you are given, what Lees and rational vertex algebra give you a modular function for free, but of course it's difficult to find such a vertex operator. And also, if it's again rational, the category of V module from a modular tensor category. So you can define invariant of three manifolds out of rational and Lees vertex algebra. So these are very nice properties. So in the past, people are mainly, because of this reason, people are mainly interested in this Lees vertex algebra. But it turned out that the vertex algebra with non-trivial associative variety are also very interesting, in particular in connection with higher dimensional quantum field theory, which I'd like to explain now. So one of the connection of vertex algebra with higher dimensional quantum field theory is the 4D 2D duality discovered by these physicists being Demos, Liendo, Piras, Rastri, and Van Ries. So what they did is the following. They considered the category of four-dimensional n equals to super conformed field theories, whatever it is, and also the category of vertex algebra, which can be identified with two-dimensional conformal field theories. So they find a map or functor from four-dimensional theory to two-dimensional theory, which is designed to do the following. So this map does the following. So there's an important invariant of this 4D theory called the Sugar index, which is a Q series. And this Q series can be obtained as a character of this vertex operator algebra. So this is nice because in a four-dimensional setting, Hilbert space is not so you cannot find a big algebra which makes Hilbert space a irreducible representation of this vertex algebra, and Hilbert space is defined as the infinitary sum of a finite dimensional representation of superconformal algebra. So it's difficult to compute something here, but here you can compute this character using a representation theory of vertex operator algebra, a vertex algebra. So this existence of such a map is already nice, but it turned out this map does much more. So there's a conjecture by Beam and Rastri that four-dimensional theory has many interesting mathematical invariants, and one of them is the Higgs branch, which is a hyperkähler cone. And this hyperkähler cone should be recovered from this vertex operator algebra as associative variety for any four-dimensional theory. So this is a widely accepted conjecture in physics. But this is quite surprising because a vertex operator algebra is a purely algebraic object, but still you recover such interesting hyperkähler cones. And direct comment more on this map V. So first of all, there's a notion of central charge physics which takes a positive value for unitary theory. And central charge of the vertex operator algebra is minus 12 of central charge of corresponding 4D theory. So this means if you start with a unitary theory, the corresponding vertex algebra is never unitary. So which means that this map is not surjective. However, so this map, so as you can see, this map goes from 4D theory to 2D theory. So it's kind of a dimensional reduction. So you might think this loses a lot of information of 4D theory, but in fact, it's conjecture that this vertex algebra is a complete invariant of 4-dimensional theory. So this map V should be injective. So this is very nice because if you think about there's no mathematical definition of 4D theory, so this preserves information for the theory, which is not which is rigorously defined mathematically. And in fact, the associated scheme is already a complete invariant. So this is another conjecture of last theory. And the vertex algebra itself is a quantization of the arc space of this associated scheme. So any vertex operator algebra admits a canonical filtration, and associated graded should be isomorphic to the coordinate ring of the arc space of this associated scheme. So this is quite a remarkable conjecture. And I have to remark that the Higgs branch itself is not a complete invariant of a 4D theory, because there are many 4D theory whose Higgs branch is a point. So unless you consider this as a scheme or fat point, you cannot distinguish by Higgs branch. So in this sense, you can think this vertex algebra as a refinement of Higgs branch. And starting from 4D theory, you can obtain a 3-dimensional theory by a so-called S1 compactification. And it's known that the Higgs branch remains the same. And if you go to 3D setting, you can use 3D mirror symmetry to identify with the Coulomb branch of the mirror theory, which is recently defined mathematically by Bravema and Finkelberg and Nakajima. So you can think a vertex operator algebra. So in this sense, you can think this vertex algebra coming from 4D theory as affinization of a Coulomb branch, which is also. Okay. And it's believed that the Higgs branch is a symplectic singularity. So this is a hyperkähler cone. So in particular, it's a symplectic variety. And so here the definition, there's a definition of a symplectic singularity. So yeah, so this is a definition of symplectic singularity. And important theorem, important fact for us is this theorem of Paladin, which says the symplectic singularity has finitely many symplectic leaves. So Higgs branch are supposed to have finitely many symplectic leaves. So it makes to consider a vertex algebra whose associated variety has finitely many symplectic leaves. So we define the following. So a vertex algebra is called quasi-lisse if its associated variety has finitely many symplectic leaves. So this is a certain finiteness condition of vertex algebra. And of course, Lisse vertex algebra is in particular quasi-lisse because a point is a trivial symplectic leaf. And what you can show for quasi-lisse vertex algebra is the following. First, you can show there exist only finitely many simple ordinary representations. So ordinary representation are those whose character makes sense. So there might be infinitely many representations, but if you're only interested on this representation whose character makes sense, then there are only finitely many. And also, for ordinary representation, this character converges to a holomorphic function on the upper half plane and satisfies a certain differential equation called a modular linear differential equation. And the point here is a modular linear differential equation is a differential equation modular form satisfied, and in particular, the solution of a modular linear differential equation is invariant under the natural action of modular group. So this theorem states a certain modularity of a character of a quasi-lisse vertex algebra, which is supposed to be the Sumy index for this theorem. So this theorem implies certain modularity of the Sumy index, which is important in physics. And but I don't. So this is slightly weaker statement than the case of a rational ones, in the sense that we don't claim that the module of this vertex span the solution space of modular linear differential equation. So the solution, this character is not quite modular, but in many cases, the character of a quasi-lisse algebra is quasi-modular if it's not modular, which means the character belongs to the ring generated by these Eisenstein series. So if it's modular, it belongs to a ring generated by E4 and E6, but you have to add E2. And for example, if you consider simplifying vertex algebra of certain level, you find the character are not modular but quasi-modular. So this is a bit surprising because this representation has a non-trivial Kazan-Lustig polynomial. So it's usually hopeless to compute character explicitly when non-trivial Kazan-Lustig polynomial appear. But in this case, you can solve modular linear differential equation and compute this character explicitly to find its quasi-modular. And the more interesting case called the quasi-lisse chiral algebra, which comes from this theory called the quasi-lisse theory, and whose associated variety or Higgs branch are Moore-Tachikawa varieties. And the Moore-Tachikawa variety is known to be a symplectic singularity, at least in type A. So we know that this is a quasi-lisse for type A. And Midas showed that this character defines a generalized multiple Q zeta values, and also he conjectured this character must be a quasi-modular. So quasi-lisse vertex algebra have quite interesting characters. And so let me, so symplectic singularity is defined in this geometric manner, but there's a quite easy way to produce a symplectic singularity from no one by the following. So if you're given a symplectic singularity, and if G is a finite group in automorphism of X, preserving the symplectic form, then O before is a symplectic singularity. So in particular, you can start with a non-singular symplectic variety. Then it's automatically has symplectic singularity. And if you find a finite group automorphism, you obtain a symplectic singularity. So in particular, you can do the following. So you can choose your favorite complex reflection group, which is generated by reflections in some vector space. So it might be a Cox-star group or a Cox-star lographic complex reflection groups. So there are many complex reflection groups. And you can consider tangent bundle to this vector space. And this is naturally a symplectic vector space. And the diagonal action of this group preserve the symplectic form. And so the quotient orbifold, which I denote M gamma, which is a spectrum of this invariant ring, has a symplectic singularity by the previous statement of Beauvais. So for each complex reflection group, we have this canonical symplectic singularity. And here is the remarkable conjecture by Bonetti, Meneghelli, and Rastri, which states the following. For any complex reflection group, there exists a vertex superalgebra with the following properties. So first of all, associative variety is isomorphic to the symplectic singularity. So in particular, this one is quasi-lisse. And it has a supersymmetry. So it can be has n equals 2 supersymmetry, or n equal with central charge determined by the degree of the invariance, fundamental invariance of this invariant ring. So this ring is known to be polynomial ring. And p bar to p rank gamma is a degree of this polynomial fundamental invariant. And when gamma is a Cox-star group, this n equals to the supersymmetry is enhanced to the small n equal 4 superconformal algebra. And there's also this has to admit a free field realization, which embeds this vertex algebra with beta gamma BC system of rank gamma. So I'd like to explain this, where this conjecture comes from. So of course, this conjecture comes from 4D 2D duality, because these people are physicists. So when gamma is the Weyl group of simple Lie algebra G, this vertex algebra is supposed to come from 4-dimensional n equal 4 or super-Yang-Mills theory with gauge group G. And then corresponding Higgs branch is the one associated with this Weyl group. So V was a map from 4D n equals to 2 superconformal field theory to the category of vertex algebra. So to define map, only n equals 2 symmetry is necessary, but this one has n equals 4 symmetry, which of course has n equals 2 symmetry. But this is more symmetry than is required to define this map, and the supersymmetry remains in the image. So the resulting vertex algebra has to have n equal 4 or symmetry. And when gamma is a crystallographic complex reflection group, then the theory comes from a vertex algebra, comes from a four-dimensional theory with n equals 3 asymmetry. But in general, otherwise we don't know whether this vertex algebra come from for this theory, but still conjecture we can define such a vertex algebra uniformly. And the aim of this talk is to prove this conjecture for the simplest case when complex reflection group is a wide group of SLN, which is just a symmetric group. So in this case, the vector space on which a symmetric group acts is the Cartan subalgebra of SLN, which is a vector space of dimension n-1. So corresponding symplectic singularity is just this one. And corresponding vertex algebra should have central charge -3 n square -1. And it has to have n equal 4 symmetry, which contains affine SL2 of level n square -1 over 2. So we'd like to somehow canonically attach such a vertex algebra to this symplectic singularity. But this is a singular space, so it's more reasonable to consider its resolution of a singularity. So in order to do that, it's more convenient to work in the GLN setting. So we embed this vector space in a Cartan subspace, a subalgebra of GLN. And then consider symmetric power of C2, which is defined in similar way. And then this is a Cartesian product of M, Sn, and cotangent to C. So this is essentially in this one. So we work on this variety instead. Then it's well known that the singularity of this one is resolved by the Hilbert scheme of n points on C2, which just so this must be a ideal. So as I said, the Hilbert scheme is just a set of ideal which satisfy this dimension condition. And so this resolution is given by this. And this is a non-singular variety. And so what we'd like to do is we'd like to construct a sheaf of a vertex algebra on this non-singular variety whose global section satisfies the required property. And there's a model for this, which was done by Kashiwara and Rukiye. They constructed a sheaf of H-adic algebras on this Hilbert scheme such that which quantize structure sheaf. And a global section is a spherical rational Schrödinger algebra associated with a symmetric group, which quantize this symmetric power of S2n. So I have only 5 minutes, right?
Yes, you have 5 minutes.
Okay, so I'd like to chiralize this Kashiwara-Rukiye construction, but naive attempt does not work due to some obstruction in constructing a sheaf of vertex algebras. So this can be seen when quite well if you consider Hilbert scheme as an Nakajima quiver variety. which is defined as a certain Hamiltonian reduction. So what Kashiwaruki did was, roughly speaking, quantize this space before Hamiltonian reduction, and then do quantized Hamiltonian reduction. And what we'd like to do is we'd like to replace so this was a wide algebra. So we want to replace a wide algebra is affine analog, which is a beta gamma system, and then do a so-called BRST reduction. But this cannot be defined, because this BRST reduction only defined when this has a right level with respect to the action of zero n hat, and this doesn't have. However, if we what Bonetti, Menegheri, Rusty suggests is the construction of a vertex superalgebra, and this solves everything, because we can add fermions here to change the label to the correct one. So yeah, so let me state our main result. So the exists sheaf of H-adic vertex algebra on the Hilbert scheme, satisfying which quantize arc space of some super variety, whose underlying topology space is the same as Hilbert scheme, and satisfy the desired properties. Okay, so, and we have checked that this is indeed the one which is so when n equals 2 and 3, Bonetti and Menegheri Rastelli described this vertex operator algebra explicitly, and we have checked this our algebra is the same as the algebra, and it's the same for the free field realization. Yes, and we can also show. So we haven't really checked in detail, but we should be, we should be able to show that the super character, which is a Schur index, is the quasimodular. And there is a quite interesting explicit conjecture character formula by physicists. Okay, maybe I stop here. Thank you so much.